Howdy everybody, welcome back to Lab Hours. Today we are doing the Continuous Conditional Distributions mini lecture. This one is hopefully going to be a shorter one because we're just taking everything that we did previously with conditional distributions back when things were discrete and we're making them continuous now. So instead of like p of x given y, we're doing f of x given y now. That's hopefully going to be a fairly simple transition for us now that we're getting used to working in like the continuous probability space over these last couple mini lectures, and we already have the experience with things like Bayes' theorem and Bayes' like formula for conditional probabilities from back a couple mini lectures. So we'll talk about building conditions into a PDF. We'll talk about, doing that for specific values in the condition, like f of y given that x is equal to 1/2. And then we'll also talk about like arbitrary values in the condition, so like f of y given that x is equal to x, and we'll talk about how the two relate, right? So let's go ahead and jump right into it. And to jump right in, I have actually gone and gotten what should be a valid joint PDF, right? And you'll remember from last time that for this PDF to be valid, this joint PDF, it will have to double integrate over these bounds to equal to 1, right? I'm going to leave that as an exercise for you because I happen to know that it is a valid joint PDF, but I would encourage you, if you doubt it, to double check, or if you're feeling weak on the last lecture, go ahead and double check. Try and see if you can double integrate this, from 0 to 2, 0 to 1, the joint PDF, dy dx. See if you can do that and get it to be equal to 1, because it should be, right? So, assuming that it is valid, if you've had time to pause the video and go check, or if you just trust me and you want to go on and you say, Tommy, let's get to it. Let's talk about building in a condition here. Because the one thing to remember really quick is that like this joint PDF is kind of representing like, this is a bad graph, right? I should actually have x down there. If you take multivariable calculus, you'll learn why I should have x here. But basically, right, like this is going to be some kind of shape that has an area underneath it, right, on this XYZ plane, okay? Because it's a PDF, it's like a 3D histogram, right? So how likely is x versus y relative to all the other possible combinations of x and y? That's what this joint PDF is doing. So if I need to build conditions into it, instead of doing what I did before, like with a probability of like, I don't know, y given that x is equal to some x, right? That was the probability of x intersect y or y intersect x, right? Because the order of intersects doesn't matter, right? Over the probability of the marginal density of x, right? The marginal probability of x, right? Of some given x value, okay? That's the old formula, right? P of x given y over px of x, or even just p of x, right? What's the probability that x happens? And then once I'm in this x universe, what's the probability that I've also hit y, right? So in the PDF world, in the joint PDF world, what this can look like is, you don't know yet because I haven't told you, but, well, you probably went to lecture, right? F of y, given that x is equal to x, I'm sure you can guess this, but it's just going to be f of x and y over the marginal density of x, right? Let's break down what this means. What is the probability of x when it's discrete? Well, in the past, if we had like a table with x's and y's, right? 0.2, 0.3, ... and I wanted the marginal probability of x, I added all of these up, and I got like x equals 0, and I got like x equals 1, right? And I got those by themselves, just by adding across x. That's exactly what I'm doing here with the marginal density of x, is whenever y changes but x doesn't, I'm just going to look at what happens to x, right? This is my new 100%. It's only where this x is equal to this x right here, right? Fx, the marginal distribution, like we've been talking about previously. And then this joint one is just the intersect, right? Like, what does the probability look like when I have this value of x and this value of y? Well, it looks like this times this value of x times this value of y squared plus this, right? So if I wanted, for example, and maybe this becomes a little bit clearer, if I plug in a specific value, like what does y look like, for example, if x is equal to like 20, right? Well, that's going to be the f of 20 and y, right? Like, we're in the world where x is equal to 20, so I need 20 to happen for x. But our new 100% is only the parts where x is equal to 20, right? This is a new conditional PDF that we're making here. Now, obviously, for this function right here, x can't be 20, but it could be something like 1/2, for example. And we'll talk about how you like calculate and get the stuff and build the condition in. But the one thing I want to point out to you really quick before we move on is that once you have built a condition into a PDF, so once you have moved from f of x and y to like f of y given that x is equal to, I don't know, 1/2, once you have moved from there, then if you want the expected value of x given that, or the expected value of y, pardon me, given that like x is equal to 1/2, you don't have to do anything special or new with the condition. All you have to do is use this thing you've already built the condition into, right? Using this step that we're going to show you in a second, all you have to do is just do the normal thing for expected value here, which would be integrate over the bounds of the thing, 0 to 1, of the thing, y, times the probability of the thing. In this case, it's asking for a specific kind of probability of the thing, this one right here, times f of y given that x is equal to 1/2 dy. This is the exact same process that we learned previously for like expected value of the thing, right? Over the bounds of the thing times the probability of the thing. This one is just asking you for a very specific type of thing in a specific probability world where x is equal to 1/2. If you find this function here, this PDF, using the steps that I will go through with you in just a second, finding the expected value, finding the variance, finding like marginal stuff, it's the exact same process, but just with this, because you have built the condition into the PDF, right? Back here, we learned how to just take the expected value of x, right? Somewhere we did that. Maybe that was in the one prior, yeah. We learned just how to take the thing of x, right? E of x by itself is just x times the probability of x when there's just the one variable. Now, expected value of y, given that x is equal to 1/2, is just y using the world of probabilities where x is equal to 1/2. So hopefully that's clear to you, and hopefully that doesn't trip you up. You don't try to do any crazy thing here with this y. Just do the exact same thing you've been doing, just with the new PDF. Build the new PDF first, then do everything you've already been doing. That's going to cover build it in. And now we're going to move on to just putting specific values into the condition and then doing it as well for arbitrary values. So let's go ahead and do that. We're going to plug a specific value into our condition here, and in fact the specific value I'd like to plug in is that x is 1/2. So let's say, what is the conditional probability density function of y given that we know x is equal to 1/2? Question mark. So there's two parts to this. We know that we need to calculate f of 1/2 and y, because that's where they intersect. That's where we get y and 1/2 at the same time, is when this happens. But then we also need to find the marginal density of x and plug in 1/2, right? We need to know what does the world look like where x is equal to 1/2. This is just like probability of b from the conditional one that we've talked about, right? Probability of x. So let's go ahead and do that. Our two parts, the first part is the denominator, and that's actually really easy. F of 1/2 and y is just plug 1/2 in for x, right? So we get 9/10 times 1/2 times y squared plus 1/5. And that's pretty easy. That's equal to 9/20 y squared plus 1/5. Okay? So we've already got part of the answer. Let's go put it in. We have 9/20 y squared plus 1/5. But what's on the denominator? That's a little bit tougher. What is fx of 1/2? Well, we don't know because we don't have the marginal probability of x yet. We don't have the marginal function of x. So let's do that really quick. And the way that we get the marginal density of x is we integrate y out of the joint PDF, right? So let's go ahead and do that. We're not touching the condition or anything. I just want to know marginal of x so that I can use it to build the condition later, right? So fx of x is equal to the integral over the bounds of y, 0 to 1, of 9/10 x y squared plus 1/5 dy. So let's go ahead and do that. Take the antiderivative, throw it into these brackets, and evaluate it from the top down to the bottom. So this, we are integrating in terms of y, so I'm going to need to change this 2 into a 3, so I need to pull that 3 out from this denominator. That's a little bit obnoxious. However, it's nice to notice if we took a derivative, y3, y to the third, to the derivative, so multiplying this by 3, had to turn it into 9/10. So we know that this is actually just 3/10, or 9/30, right? So 3/10 x y to the third, right? Because if I were to take a derivative of this 3 would come down, multiply by this, that'd give me 9/10. This would turn into a 2. That gives me this right here. That means I have the correct antiderivative, which is super nice, right? And then 1/5 plus 1/5, that's going to turn into plus 1/5 y, because again, I have a y to the 0 here right now. That's just 1. So I need to take a 1 from the denominator, turn it into y to the first, which obviously doesn't change it, right? And then we're going to evaluate that from 1 to 0. Now the nice thing about this 0 bound here is that plugging in 0 for y is going to cancel this entirely. So I can just plug in 1 for y and go from there. And we find out when I plug in 1 from y, 1 cubed is just 1, 1 is just 1. So we're going to get 3/10 x plus 1/5. Super nice, super simple. So what is fx of 1/2? Well, now that I have fx, I can just plug it in. It's 3/10 times 1/2 plus 1/5, which is going to be equal to 3/20 plus 1/5, or 3/20 plus 4/20, which is equal to 7/20, right? And if you're following along on paper, you can go ahead and check that as well if you'd like. So fx of 1/2 here down on the bottom is going to give me 7/20. Right? fx of 1/2 is 7/20. And then there's a way we can simplify this. So if I take 9/20 y squared plus 1/5, and I multiply it by the reciprocal of the denominator, that's going to be equivalent, so that's 20/7. That is going to give me, well, let's see, this 20 is going to cancel, right? So that's just 9y squared. And then this 20 is going to turn into a 4, and this 5 is going to cancel. So that will be 9y squared plus 4/7, right? Oh, it's not 9y squared. Pardon me. That's 9/7 y squared. Because why? Because this 20 canceled, but the 7 doesn't cancel with anything, so it just turns into 9/7, right? That could have been a big deal. But now that we've got the correct answer here, 9/7 y squared plus 4/7, you can see that like algebra errors are going to take you down on this stuff half the time anyway, right? So that is how you find a conditional probability density function for a specific value of like the condition, right? X equals 1/2. This is what y looks like. 9/7 y squared plus 4/7. Easy peasy, right? Super simple. Pardon. And by super simple, of course, I don't mean that it's like simple to remember, but once you know the pieces and you remember how to find the pieces of the pieces, then it's just plug and chug at that point, right? So if you can just get this to that, to that, to that, you have this with plug and chug. Super simple stuff after you figure out how to set it up, right? That's kind of always how it goes. So we've covered how to do specific values in the condition. Let's talk about just solving this for arbitrary values in the condition. So what would this look like if I just want to know what y looks like, given that we know what x looks like, okay? We're going to start the problem the same way. This is the intersect of x and y over an unknown value of x, pardon. So I just need fx of x on the bottom. The interesting thing about this is that this is actually almost easier in that we've already calculated all of the pieces that we need, right? So if I follow the same color scheme, the numerator is just f of xy, which is just what we have here, right? 9/10 xy squared plus 1/5. I don't have to do anything else for that. Super nice. What about fx of x? Well, the nice thing is we already figured it out. We integrated the y out already, and we got 3/10 x plus 1/5. fx of x is equal to 3/10 x plus 1/5, right? Yeah. So this conditional probability with an arbitrary value, you just slap the numerator over the denominator, 9/10 xy squared plus 1/5 over 3/10 x plus 1/5, right? And so let me just multiply everything in there by 10 really quick, just to make it a little bit simpler and nicer to deal with. That would give me 9xy squared plus 2 over 3x plus 2. Now, if we've done this right, if I were to plug in 1/2 for x, we should get the same number as we got over here when we were actually using 1/2, right? Because you realize that's kind of all we did. But if I have the correct setup here, the usefulness about doing an arbitrary value is that now I can just plug in anything I want for x, right? So let's just double check really quick to make sure that our math was correct here, to make sure that we set this up right. What is fy of x? What is f of y given that x is equal to 1/2? Well, that would be equal to, 9 times 1/2 times y squared plus 2 over 3 times 1/2 plus 2, which is equal to 9/2 y squared plus 2. And I'm just going to multiply by the reciprocal straight off the top this time. 3 times 1/2 is 3/2, 2 is 4/2, so that means 7/2 was on the bottom, so I'm going to multiply everything by 2/7, right? That's the same as putting 7/2 in the denominator. And what y squared, 9/7 y squared. 2 times 2 is 4 over 7 is plus 4/7. And you'll notice those two numbers are, well, those two formulas are exactly the same. Functions, they're functions, not just formulas, right? They're exactly the same thing, which means that we did our job correctly. Super cool. Now you might be wondering, well, what does y look like if x is like less than 1/2, or if it's less than something? That's going to be outside of the scope of this video. I know that there's like a homework problem that does this, but what you have to do is you actually have to go back and change this function, right? You have to readjust for a k, or you have to do the following, right? You have to do like f of xy over like an integral over some new bounds. And like I know that there's a homework problem if you're still in Econ 378, like at BYU, if things haven't changed. There's like a homework problem that asks you to do that. Go ask the TA for help on that one. But you should be able to, using this kind of idea, where instead of x equals x, you have x is like less than some certain value of x. You should be able to figure out what to put in there based on the other videos that we've done. But I'm running out of time for this one, so I'm going to leave that one for you as an exercise. And maybe the problem isn't even there anymore. You really won't use it that much in the future anyway. So at least not from what I can tell. So that is going to cover the continuous conditional distributions mini lecture. That's our Tommy triple. We built a condition into the PDF and talked about what you can do with that after you build it in. We talked about building it in with specific values, and then also building it in with arbitrary values so that you can plug in specific values later. That is going to be it for today. Hopefully you will join us next time in lab hours, where we're going to start getting into the really, really fun stuff in the course, which is like the common probability density functions, or the distributions, right? That like have super cool special properties that let us do super cool special things with them. We'll talk about the Bernoulli distribution, the uniform distribution, and then we're going to get into the normal distribution, which is where this class really starts to pick up. So hopefully we'll see you next time in lab hours. As always, if you have any questions, if you're in the class, email tmorg@ta@gmail.com. And if you're not in the class, email labhours@tmorg.org. As always, you can also leave your questions in the comments. Leave the video a like. Be sure to subscribe if you like to see them and like to know when they pop out. And thank you so much for watching. Have a wonderful time, and we'll see you next time, hopefully. Bye-bye.